Okay, so good morning, everyone. This is week 11. So we have 5 lectures left for this course. So the calculations will become more and more intensive. We will have more to do. And hopefully by now you have really gained the skills to do all this standard treatment. So I will go faster. And also reading week is coming up. And as of today, today's attendance is not very good. That's why I need to say it here for this for those of you watching the video. Now these videos are really supposed for revision. They are not something you should watch at the end of the course. Okay, you are supposed to learn according to the pace of the semester, right? So you try to get knowledge and then do the assignment and then learn this course like this. So this is also how I want to do it. Another complaint is this: exercise class attendance was also very appalling. I received the report from the TA that we have like 4, 6, and 4 students. 6 for the first slot last Thursday and 4 for the second slot, something like that. Okay, and that is also not very good. Okay, so if you're watching the video, please understand that I don't really like to see this. Okay, so after complaining about this, now come back to the business. We have assignment 8 uploaded. This is a long assignment. This assignment is practically nearly equivalent to 2 assignments. So this one is quite long. So you should start. I gave it out earlier, right? So you have more than 1 week. You have 1.5 weeks to do this. And then there's another assignment at the end of the reading week. Okay, which is about this assignment 9 will be available. So you are requested to think about statistical mechanics during the reading week. Okay, so that will be 11, also Monday. Okay, and then exercise classes. This is getting more and more essential because a lot of things I will ask TA to derive. For example, something a little bit more routine, but you already grabbed the concept, and we will ask the TA to help. So please go to the exercise class. So for example, I would tell you what is what I asked TA to do this week. So a bit of recap. Last lecture, we begin to talk about gas, indistinguishable particles. So this is some result we derive. There are a few points that you should really pay attention. So here, the first thing is the dimensionality. Okay, I say 3D. And you should convince yourself that if you do the calculation in 1D, in 2D, you get very different expressions. And you are asked to do something like this in the assignment. This is a very standard thing. So the density of states, in particular in 3D, has this square root dependence. And what is this energy dependence? The functional form of, apart from the fact that the multiplier in front can be different, the prefactor can be different, the energy, the functional form of the dependence on the energy can also be different. So you need to be very careful. The dimensionality is key, right? So just think about how we count the state. And second, this is a bit of notation. It's not an issue. It's something in the note, in the printed note, the PDF I uploaded, I use this symbol. I just copy from my note. So this is equation 10.8. Okay, and I believe in the lecture I use a different symbol. Okay, so I may probably use N, big N, to denote the number. This is the number of states. So in the note, I kind of use G. I think that is a better notation. Okay, N, I use N if I had used N last lecture. Just be careful. This is not the total number of particles. Okay, so probably uh, just be very careful about the meaning here. Okay, so they really mean the same thing. G is the number of states below a certain threshold in energy. This threshold in energy is epsilon, and we kind of we can choose a way to define this threshold. For example, at the end of last lecture, we did some number crunching. I told you I will give you some thermal energy. This thermal energy is room temperature, so you can just say epsilon is of the order of kBT, where T is 300 Kelvin. You plug it in, you know there's a threshold in energy, and this threshold uniquely defines some kind of a radius. Right? That's why you see this radius coming in, and this radius, some radius are so any states enclosed by the sphere defined by this radius will satisfy this meaning, number of states below epsilon. That's how we did the calculation. Okay, and then here this is the quantum numbers you use, nx, ny, and nz in 3D. And to specify a state, you need to give out all these coordinates, nx, ny, and nz. So this would be a unique state. So for example, this is nx equals 2, ny equals 2. Okay, in the 2D equivalent. Okay, so each one of these is an allowed state, and you are asked how many of these points you have below a certain energy E. Okay, and after that, because this radius is large, as you have seen, we have a lot of states. Then we can just treat these points as continuous rather than discrete. That's the point. Then we have something called the density of states, and this is a good thing. The density of states is an expression. This is the expression we got, and this is expression 10.10 in the note. And we can do a lot with this kind of expression. If we really treat it as discrete states, that is actually harder to manipulate. If we have a continuous distribution, we can do integration. That is a lot easier. Okay, and this GE, density of state, GE, takes this meaning. This is something I stressed. So GE multiplies by DE or epsilon. Okay, okay. This G of epsilon times D of epsilon is a number. Okay, this is a dimensionless number, a number without unit. This takes the meaning of number of states between epsilon and epsilon plus D epsilon. Okay, when I say E, I really mean the same thing. Okay, sometimes I slipped a bit. Okay, now I think some of you have already seen this in QM course. I just want to say that this is good. You have seen it at least twice. That would be good, but don't worry, you see it many times for future courses. In particular, if you take solid state physics. If you take solid state physics, this is the part that you cannot escape. No, you cannot escape from density of states. So I want to make one distinction right away. So here, you remember how we treat this? We basically talk about the particle in the box, and we didn't solve the Schrodinger equation from scratch. I just give you the answer. There's something which I didn't say. Is the following: when we really talk about a box with this 1D drawing, 1D equivalent drawing, box really means we use a boundary condition. You know, when you do quantum mechanics, when you solve all this problem, you need to mention what is your boundary condition. This is something I didn't say, but you can patch it now. I really means box, which means the particle cannot escape from the box. This is infinity. And therefore, I have to demand, what do I have to demand? I have to demand my wave function to vanish at 0, okay? And I have to also demand the wave function to vanish at A, so the particle cannot escape. So this is my boundary condition. And if you do this, you get standing wave. This is all this sine and cosine, and depending on where you put the zero, you get one of these solutions. So we get standing wave solution. Okay, this is what we did, exactly what we did. And I don't want to repeat the whole thing, but there's another type of boundary condition which we use a lot, particularly in solid state physics, and we are going to use it again. We're going to develop something similar. Okay, that is called the periodic boundary condition. This is periodic boundary condition. Now, this periodic boundary condition is something I will ask TA to try to derive in the exercise class. I don't want to start from scratch, and I want to use it right away when I talk about metal. When I talk about metal, this enters the solid state physics, and therefore we are going to really use the most common terminology. So in solid state physics, we like to use the periodic boundary condition. What is the periodic boundary condition? Now, we usually talk about electrons in a box, right? So that box is our material, is let's say our metal, right? That is a box, and our electrons is traveling inside this piece of metal. So that is a particle being electron, the box being the sample, the metal. And what we like to discuss is we assume if we are not looking at the physics of the boundary, that's to say, if we are not worrying about the surface physics, we just want to look at the bulk, we assume the electron, when it travels to A, it will come back to zero. Okay, that is the meaning of boundary. That's the meaning of periodic boundary. So I go to A. When I hit A, I actually also come back from zero. Okay, so how do I write this result? Pay attention. So in that case, I want my wave function at zero, right? Or I go to zero. I go to zero, I basically come back from A. So this is what I need. Okay, whatever values, I don't need to demand it to be zero. Okay, and look at the distinction between them. And if you solve it using this boundary condition, the solution is traveling wave. You get exponential. So this is a traveling wave. Okay, so keep this in mind when you deal with this. Okay, so coming back to here, what did we do after we used the box boundary condition to develop all this? Sorry. One more point. If you use the periodic boundary condition, you might wonder, does it affect all this counting? The answer is yes, you affect certain element of the counting, and that is what you should pay attention. But the end result, that is to say, once I ask you what is the density of states, you find that you get very similar expression. Okay, but there's something for you to appreciate. Okay, so compare. Your task on Thursday is to compare, or in the future when we do this different way to treat the boundary condition, what is the same and what are the same and what are the different. Okay, so surely something to do with physics must be the same, because this is just a different way to look at the same problem. Okay, now, okay, and last time at the end of the lecture, we did the counting. We put in some real number, right? We put in helium, we put in the mass of helium, we take a volume, and this is our conclusion. This is the conclusion from that number crunching. We find that for the gas, we can, for the gas at STP, standard temperature and pressure, we can have this easily. We can have this conclusion easily. Okay, the number of states, the number of energy states available is much larger than the number of particles that we need to deal with. Okay, and it's very reasonable at this point to ask, how do you violate this condition? And that is the stuff you will see at the end of today's lecture. Okay, so now coming back to the case of this, The next question to ask is, how do we deal with the distribution function, the equilibrium distribution function? Okay, so we need to develop some counting again. Okay, keep this in mind. We are dealing with a distribution function for gas. Okay, indistinguishable particle. So here's the picture. This is what I propose. We are going to develop this bundle, the concept of bundle. I'm going to call this the kth bundle. All right. So we already know from the last line of this chapter, we know we have a lot of energy states. So we know we have a lot of energy states. So I'm going to draw. These are the energy states. They are available for us. And how do we deal with this? Since there are so many of them, we can just group. Imagine that we can just group them. Okay, so I'm going to, for example, take this and cut it into some boxes. This is one of the box, which I call the kth box, and the one above will be k plus 1, and the one below, this one will be k minus 1. Okay, so this is the meaning. This k is just a way for counting. Okay, so in this bundle, this energy will be so closely spaced that I can take one of the energies. Let's say we take the average, the one in the middle. That will have the energy epsilon k. And this epsilon k will be a good representation of all the other energy levels, energy states in the same bundle. Okay, you get this point? So let me use different color. I'm going to take this and draw it like this. So this will be my energy k. And this one will have a different energy, k minus 1. And this one will be my energy k plus 1. Okay, and inside this bundle, there are so many of them that I will use a different symbol to denote them. Okay, how many of them do I have? I have gk of them. Okay, and this is gk plus 1. And this is gk minus 1. Okay, this is the number of states. So you have gk of these states. All of them can be approximately described by epsilon k. Okay. Again, this is something you need to put some numbers in to see that this is actually quite a reasonable approximation, because there are so many of them closely spaced. So the deviation between epsilon k and the top of the bundle is not important. And likewise, the one at the bottom. Okay. And for the bundle, we have nk particles to distribute. Okay, so let's write out what we want. We want to consider this situation, and then we want to imagine. This is like a thought experiment. As I say, you can put in some numbers to find out what is the requirement for all these numbers. But here we can just really assume this is really just a matter of convenience. You have all these energy levels, there's so many of them. Why do we want to care about all of them? Because it's not really useful. We don't have so many particles to deal with anyway. So why don't we just group them together for convenience? Okay, so the important point is for convenience. Okay, so we need to imagine for this treatment to work, we want our nk to be large. We still want a large number of particles. Okay, how large? Large such that Stirling's approximation work. This is not that difficult to satisfy. Now, I gave you some number last time. When I reached this line, I told you we have a lot of states compared with the number of particles. I remember I gave you 7 million states and 35 particles. I think I used the example of population of Hong Kong. We have 7 million people in Hong Kong, and we only have 35 cars, let's say. Okay, but this is a ratio, right? And before I took this ratio, you remember the number was huge at there, right? 10 to the 20, that kind of number, right? So this is not difficult to satisfy. Okay, even if I chop it up, 10 to the 20, 10 to the 29, wait a minute, let me get this number. This number is so huge that even if I chop it into 10,000 different bundles, I will still satisfy this huge number. Right? Yes, 10 to the 22. And the other one, number of states, 10 to the 27. So this first approximation is not that difficult to satisfy. I still have a lot of particles. Okay, second, I also want, in a given bundle, I want my GK to be large. Why? Because I want to use Stirling approximation. Okay, that is to say, in the bundle, I have a lot of states, but not too large, not large enough for Stirling to work. That is not that difficult. Stirling is, if you have 100, is already quite a good approximation, but not too large. Why? Because if it's too large, this is, imagine this box, this will be very thick. So there will be some of the energy levels will be far away from epsilon K. Okay, so the reason we don't want this to be too large is because we want epsilon K to be a good representation, to be a good representation of all energy states in the bundle, in the entire bundle. Okay, and now we are ready to do the statistics. What is the question to ask? Okay, so let's look at one bundle. If we know how to solve the problem for one bundle, we know how to deal with the remaining bundles. Okay, so if we just focus first on the kth bundle and ask yourself, how many ways do we have to put NK particles in GK level? So look at these pictures here. Now I have GK's level. This is this symbol kind of hint that this is a bit like degeneracy, right? In fact, if I take this concept, this is really taking the meaning of degeneracy. I have GK of energy states. All of them are approximated by energy epsilon K. Okay, so now imagine that I have GK of them. And I have NK particles in this bundle. How many different ways can I arrange these NK particles? Okay, so this is the question. How many, or how to arrange NK particles in GK levels or states or boxes. Okay, this is the part that that is fun. How do we deal with this? Now, suppose I have 3 energy levels. Okay, listen carefully. I'm gonna draw some cartoon now. I have 3 energy levels. I'm going to call this energy level 1. Okay, I don't need to label. 2 and 3. Okay, suppose this is of the order of increasing energy when I go from left to right. Okay, I have 3 boxes, unique boxes, which means I can put my particles inside, and I have I don't know how many particles. Right now I don't need this dilute limit approximation. I just want to demonstrate the point. Let's say I also have 3, and I also have 3 particles. So I can put it like this, right? I can put 1 particle here, 1 particle here, 1 particle here. This is one way to do things. I can also do 1, 1, 1. Or I can put all of them into the same box. And right now, I don't care about the character of these particles. Let's just assume I'm allowed to put this. I just want you to appreciate how to write down, how to do the probability theory. Okay, so this scenario, if I have 3 boxes, how do I define 3 boxes? To define 3 boxes, I just need 2 partitions, right? So this is equivalent to saying that if I have 2 partitions, I can uniquely define 3 spaces. Okay, so this picture I drew here will, for example, be this. This is one scenario, right? Okay, so let me bring this. So this is what we need. So that is the point. If I have GK energy level, if I take this picture, and rotate by 90 degrees, you can see this is really mimic our physics, right? I have 3 energy levels, but I can put 2 particles here, 1 particle here, right? This is really what we want. Okay, so if I have GK energy levels, so GK levels, I will need GK minus 1 partitions to describe the full picture. Okay, so that's answering this question now. This question, so the answer is this. So how do I do that? How do I arrange? I will have to look at GK minus 1 partition. So this is the vertical line. And then I have NK particle. I cannot do much. And this is NK particles. I will use dot. So this question basically is equivalent to asking how many different ways can I arrange NK dots and GK minus 1 vertical lines along a one-dimensional line. Okay, just like what I drew here. Okay, so let's look at some picture. So here is my picture. I have it in the note as well. All right, so this is a picture. This is a bit more. This is 1, 2, 3, 4, 5. This is 6. GK is 6. NK is 3. How many different ways can I align 3 dots and 5 lines along a straight line? Okay, so these are the 2 different scenarios. And how do you do this? You know very well. You know how to do it. Maybe you haven't realized. I hope now you very quickly you will realize this is the good old friend. I'm just gonna call this head and call this tail. Okay, the dot is like the head of the coin, and the vertical line is like the tail of the coin. Okay, so the answer is clear. I'm going to use the same symbol. How many ways can I arrange this? I have now for the coin, you know, this is the total number of coin divided by how many head you obtain, and this is the number of head, divided by how many number of tail you get, right? We have seen this, and this is, I called this is the coin problem. All right, so just copy the same idea. How many total number of coin do I have? I would just treat them as coin, right? So in total, I will have NK plus GK minus 1. I just have to sum these 2. This is a total. Okay, and then how many head? Okay, head will be NK. How many tail? Tail is partition, so there will be GK minus 1 of them. Okay, so remember what is behind this. We cannot, now we can distinguish the difference between a coin, the difference between a particle and a partition, but we cannot distinguish between the different particles. Okay, so that is the meaning. That's why we have to do it this way. And you can convince yourself that this is indeed different from this. Okay, so if this will give you all the possible combination. Okay, and finally, I will denote this K here. This is for the kth bundle, and the full answer is here. And for the total, this is for now we look at the entire system. The entire system will require us to go and look at different bundle, right? So starting from K equals 1 until, I don't know, K equals whatever number we decide to chop up the energy level. Okay, so now here's the question for you. What is the relationship between this and this? I would like something in the chat, private message. Okay, so this is the big omega without any label. This is a total. I don't want to introduce more symbols. So this is a total number of different arrangements taking into account the entire system. And we have already worked out how to deal with the kth bundle, but we have many bundles. And what is the relationship between the two? Okay, you can just type. The answer is very, okay, I see the standard 2 kind of answers, which means half of them will be wrong. Again, another one. That's amazing. Okay, more. Now if I vote, I get 50-50. Yeah. So half of you is perfectly correct. The other half is completely wrong. More. I would like, I want to protect your privacy. Now you have your name attached to the answer, so I cannot screenshot for you. Now the correct answer is a product. So obviously half of you think really correctly. Now product is correct. The other half tell me is summation. Okay, then this is fun. You need to, those who say, actually for both of you, for both group, it's really important to convince yourself why this becomes a product. Okay, so this is something you have to think through, because this is really coming from probability theory. I can tell you the answer, but that would be less meaningful. So think about this. Why not this? This is the thought process you have to go through. Okay, why? All right, don't need to give me the answer, but think about this. And the answer, of course, is available on any standard textbook. Now, we need to get this correct. Otherwise, the whole treatment will break down. So this is a question mark, another question mark. Why not the summation? Okay, so I need to then I only need these 2 lines, and I can begin to find the equilibrium distribution. But before that, I want some approximation made here. I also want to give you a preview. Now I can now one of the possibilities here, of course, it will be for example, I can have a partition, and I can put all 3 particles here for this simple example I get. This is a case when we deal with boson. And now we don't really say too much about the character of the particle. We don't know whether it's fermion or whether it's boson. There's a reason behind this. At this moment, we are doing everything completely fine, but soon we will have to really distinguish between these two species. And there we are going to repeat the calculation again. We are going to deal with the situation where we allowed multiple particles, 1 million of them, all coming to the same energy state. We need to include this possibility, and that is when we need to come back to this calculation again. Actually, this will happen soon. This will happen on Wednesday. On Wednesday, we are going to introduce quantum statistics. Okay. And I will also explain why we call this quantum statistics. So right now, just let's continue our treatment. All right, so I will begin to make approximation. So I will draw some line here. I will start the approximation. What approximation? Approximation for the dilute gas. Will begin here. Remember, up to here, if you are paying attention, you know I'm talking about NK and GK being large numbers. I already put up there the 2 points here. I've been where is it? Here, the large number. I also actually did not really demand the number of particles to be that much smaller than G sub K. I mentioned it, but this calculation does not take this into account. Right? For example, here I draw 3 boxes and 3 particles. Right, so here I drew like 6 boxes, 5 partitions, 6 boxes, and 3 particles, and I came out with this number. And this coin approximation doesn't matter how many coins, right? I did not really invoke the big number yet. Sorry, I did not really invoke the dilute limit. Okay, so the approximation for the dilute limit will begin now. Okay, what are the way? How do we do it, and what advantages can we gain? So now we have GK and NK to deal with. So these are the large numbers. Be careful. Okay, remember. So these are large number. And furthermore, for the dilute case, I would assume NK, number of particles in the case bundle, to be much less than the number of available energy states. All right, so then for the case bundle, I can make approximation. So what is the first approximation I can make? I come back up to look at this expression right at the top. Okay, this expression right at the top of your screen. It tells me NK is a big number, GK is a big number. So who cares about this -1? Okay, so that is the first thing I can Q. I will have NK plus GK factorial. And likewise, I have NK factorial and GK -1. Who cares about this -1? Nobody. Okay, so this is my first line. Okay, so this approximation comes from the big number. And now, I want to rewrite this for you. Okay, I will make your revision easier. Okay, I will write that later. You will see why. Okay, here now this is approximation. Now the next line is exact. I'm going to look at it like this. I'm going to look at this as I will first. I need a very long line, and I don't want to deal with the denominator. At the top, I can look at it this way. I can look at this as some number n plus k, nk plus gk. Right, factorial. I know how to deal with factorial, and I can just write it as a product like this. Right, the largest number, or n factorial, of course, start from n. Oh, sorry. Let's pick a different. some big number, 1000 factorial will start from 1000 multiplied by 999. So I take this number minus 1. Okay, and then I keep on doing this until I hit GK. And then I stop. Okay, right? I start from 1000 factorial, which is equivalent to 1000 multiplied by 999 multiplied by 998. And then when I hit, for example, 500, I stop. I put 500 factorial. So the term before this will be 501. What is 501? It will be GK plus 1. Okay. And how many of them? How many terms do I have between here and here? This is NK, right? GK plus NK. Okay, so I have altogether NK terms here. All right, and now I invoke the second approximation. That is the dilute limit. So I change color. Approximation. Okay, so now I write it here for you. I will write. I will make the note a little bit better for you. Okay, this is everything in black is a large number approximation, and now in orange this is dilute limit approximation, dilute. So I have NK is much smaller. Okay, so NK is much smaller than G sub K. So who cares about NK? So I will just put GK. Okay, now if you then look at GK, and what you have is NK minus 1, which is even smaller than NK, then who cares about that? So you just keep repeatedly take away numbers from NK. So all these will become GK multiplied together. And you have n of them. And now this is obvious. This GK is much larger than 1. Who cares about 1? Right? So you have GK of them. Okay. And don't forget, you then have to multiply by your GK factorial. But you have a nice cancellation now. You have NK factorial, you have GK factorial. Okay, so you cancel your GK factorial. This is exact. The next line is exact. How many of them do I have? I have NK, so I raise it to the power of NK. And then divide by NK factorial. That's it. Okay, so a really big warning for you is this result, last line, you obtain is only for dilute gas. Okay. All right. So the next thing is to put together everything. So I have what is everything? Everything actually is not really new. It's this line here. So we need to look at the total system, which is the product of omega sub k. Omega sub k we just found out is this guy. Okay, and that is enough for us to do the optimization. So it's a bit like all the standard tricks we have used before. Once we get to this point, the next thing is to maximize omega or log omega equivalently, subject to some constraint. So we just repeat the same machinery and we will get the equilibrium distribution for the dilute gas. And for the dilute gas, so now I want to treat the dilute gas. So stupid this thing. 0, 1, 2, 3, 4. Okay, so I want to take the last last expression here and begin to do the maximization. This. This is really annoying me. And this is I pay for this service. Okay, this equilibrium distribution for function for the dilute gas. Okay. Standard thing, we need to maximize omega or equivalently log omega, subject to the constraint. What are the constraints? The total number of particles is fixed. Okay, I have a lot of gas particle, but still I want them to be fixed, even though I cannot recognize the difference between them, and I want the total internal energy to be a constant. Okay, and how do we do this now? The way now I hope you appreciate. Now when we do the bundle, you can see this is the whole machinery is identical to the case when we talk about distinguishable particle. Because how do I work out N? Rather than using K to label a particular energy state, this takes the meaning of the bundle. So within the bundle, we cannot tell the difference between the particles. But fine, I don't care, because I just need to know how many are there in the bundle. Okay, so this is how I do this. I go and count all the bundles, and for each bundle, I count how many gas particle. And likewise, I can do the same. This is the average energy for the bundle, and I know how many particles are there, and I form the product, and then sum over all of them, I get this. So if you now the mathematics is the same, but the meaning is very different. Okay, so let's do it, and do it quite quickly. Okay, so we have this. This is the result we learned. Gk raised to the power of nk divided by nk factorial. All right, so what is the log of this? This is what we need to spend time to deal with. If you take the log, now here's the problem for the half of the students who say summation. Here you get it wrong. Okay, so when you take the log, you have this product to deal with. So you take the log, you form the sum, and this is sum of nk log g, nk log g sub k, and minus the sum of log nk factorial. All right, so there's a bad writing. I should write it a little bit here. Okay, so nothing much to do really. You can have nk log gk, and here might as well do the Stirling approximation. So I will pull out this summation, and here I have minus nk log nk plus nk. There's minus sign here. Okay, and this is a little bit of simplification, not much. I will have nk log of gk. There's a minus sign here, so I want to group these first two terms together. Okay, and then what is this? What is sum over nk? Sum over nk is n, so let's put it. Okay, and this is the expression that we need. So let's box it. Box it like this. Okay, we will need it again later. So right now we do the standard thing. We take the d log. Okay, this d log will give me a dnk on the other side. You remember how to do this? So let's quickly do it. We have sum over k. So here, this is you take the differential. You will have log. If you differentiate nk, you get 1. We do this differential with respect to nk. Okay, so you have gk divided by nk and dnk. Okay, plus, now this is a product rule, so now you keep nk and you differentiate the log. So you have 1 over whatever in the argument. Then you have you differentiate the argument, you have gk, and then you have 1 over nk to differentiate. You have 1 over nk square. Don't forget your dnk. Okay. Okay, and then this is a constant, so you plus 0. Okay, and now there are more simplification you can do. So you have nk times nk. You have nk squared, so this is gone. And you have gk divided by gk. This is gone. Okay, now again, one more time. Tell me, what is the second term? This is the first term. This is the second term. What is the result for the second term? In the private chat. So when you are typing, I'm writing the first term. The first term is log of gk divided by nk times dnk plus, why do I expect a quick answer, really quick. I want a beautiful answer. So far I see -1 minus n dn question mark 0. Any more? Thank you for look, this summation sign, will see the dnk. Okay, sum over dnk is d big N, right? If you take the differential here, dn is sum over dnk, but dn is 0. So I want, this is the answer I want. I want a beautiful 0. Okay, so this is I highlight this for you. So this one in the end is this. We have seen it twice. It's not this is I don't know, this is something you should really it's not easy to recognize this perhaps, and that's why in a lot of occasions I see very messy calculation from students, because they fail to realize this. So they carry this dnk and somehow they get confused and lost, and the whole thing is a mess. So this is maybe one of the big tips I should give you. Okay, try to memorize this, of course with some good reasoning. Okay. All right, so we are nearly there. What do we have? Okay, so let's change color here. This is a nice color. Okay, you have the expression for d log. Then we are done. So we start to do the optimization. This is optimization. Optimization. It will begin here. Still, we are talking about dilute gas. So again, this is about the sign convention. And this sign convention is consistent with my note. So I'm going to set this to 0. I want to optimize this subject to constraint that dn is 0. So I put the Lagrange multiplier alpha and du is 0. So this is my whole thing to do. Okay, so let's One more time, write down everything. So all this term will have sum over d and k. So let me pull this out. Okay, the first term will have a minus log, right? There's a minus sign here, so there's a minus log of gk divided by nk. And the second term we just talked about, that is sum over, this is actually this guy, so I would only have alpha. And how do I do du? Du will be the product of dnk and ek. This is an ensemble that we are not allowed to change volume. So that's it. That's all we have. Okay, so and therefore we can extract the condition. That is, we will have log of gk. This whole thing in the square bracket is 0. Okay, so I will have minus alpha minus beta epsilon k. All right, so this is the usual way we write it, and therefore we would like to keep this log like this and put the minus sign in, so we can write like this. Nk divided by gk is e to the minus alpha times e to the minus beta epsilon k. Okay, or more commonly, this is written like this. So more commonly, this is written like this. Nk is gk e to the minus alpha, which we call a. It takes the same meaning, this Lagrange multiplier. And this also takes the same meaning as related to the inverse temperature. Okay, I'm not going to prove it again, but they are the same meaning. So I will write. So this is E epsilon k divided by kBt. So this is my beta. Okay, so this is the same as before, but of course all these meaning are different. This k takes different meaning, but otherwise this is the same expression mathematically. So this is again Boltzmann. You see Boltzmann again, your good old friend. Okay, now you learn the density of state, so I will right away make a remark. This is for the discrete bundles, right? I can count k equals 1, k equals 2, k equals 3 bundle. If I have a lot of energy levels, if I treat them as continuous across the bundle even, I can also write it like this. I can write the number of energy states between E and, sorry, this n is the number of particles. Sorry, the number of particles between E and E plus dE will be this product. Okay, and this product is related to G. Now this is the G we spend time to develop. This is the GEDE. This GE is the complicated expression at the beginning of the lecture I gave you at the recap slide. Okay, you plug this in and you can do a lot of calculations now. Okay, and then we have this e to the minus exponential function. This is exponential of E over kBt. Okay, you drop the subscript k, and then this e to the alpha, this is the normalization A. Okay, and you know you can do a lot of calculation. For example, you can obtain this A by this. So A, if you integrate from 0 to infinity, you must be able to count to cover all particles. So this must give you n. Okay, so this is same as how you do normalization in quantum mechanics. You count everybody. Right? There you talk about the probability of finding the particles. So you evaluate the wave function square. But here this takes the meaning of number of particle anyway. Okay, so this is how you do it. You get the total number of particle. Okay, so I have a lot of exciting things to cover today. So let's take a short break. This one, I really mean a short break. So just enough to go to a bathroom. Okay, so let's come back at 12:41. Okay, let's continue. So first, this is the expression of G of E. Okay, so this is the same thing I showed at the beginning of the lecture and something we derived last time. Okay, so now this is the form that I will use to do calculation because it's very convenient. You can integrate when you have discrete levels or discrete numbers like this is hard. Okay, so let's proceed from here. So what is the first thing we want to look at? The first thing we want to look at is all this partition function again. So this is partition function for the gas. Okay, so this is I will again do it very carefully. I put the descriptor here. So this is for the single particle. We have a lot of gas. We cannot distinguish between the gas particle, but we can still pick one of the gas and ask what are the possibility for this particular particle. Okay, we can do it this way. So this is again to remind you, this is for gas. Okay, so in this spirit, the single particle partition function, we will ask what is the possibility, and this possibility turns out to be the same thing again, right? So we can write down all the possible energy that a given gas particle can occupy, right? So it's single particle. So we pick one gas particle and ask this question. Okay, and then for each of the bundle, there are a lot of possibilities. Okay, so this is mathematically identical, but again, the meaning is very different. Again, maybe for a future reference, not too distant future, I would write down the continuous form of partition function in this case. So in this case, sum over k means I really evaluate everybody. So if I have continuous, then this G becomes GEDE, right? This E sub k becomes just E or epsilon. Okay, and how do I sum? The way to sum is to integrate. Okay, then you integrate over all possible energy E. Okay, so this is how we do it. Okay, you have the partition function. The next thing is to ask about the same question again. How do I get the internal energy? How do I get the entropy? And so on. Okay, so the point to keep in mind is this: everything looks identical mathematically, but the meaning is different, as I explained to you. So this exercise must eventually allows us to discover something new. So this is what we aim to do. We are trying to find what is this something new about the gas that we did not have when we talk about the localized distinguishable particles. So I have internal energy U. How do I write it? I write it like this. Standard, very standard definition. Okay, so I will have to plug in E sub k, E sub k, and N sub k. What is N sub k? N sub k is what we just obtained, right? Remember how we did things earlier? After we get the equilibrium distribution function, we play with this, right? So N sub k, we know how to write it. That is this guy. E sub k divided by kBT. Okay, and then you use the same treatment. Now, mathematically, this is even identical. So really nothing new technically. Okay, so you get the same expression, log of this. Okay, this is 1. Now we deal with u, and the next thing we should do is to deal with n, right? Because these are the two summation that we wrote earlier here. Okay, so now let's do that. And again, same thing. You plug in the equilibrium, you plug in this expression for the equilibrium distribution. You find a form that we want. This is equivalent to this, right? So everything, what we are doing now is to try to rewrite all these thermodynamic functional states as a function of the partition function. Okay, so this is what we have. Okay, so entropy next. Entropy, how do you do that? Remind yourself, how do you do this? You take the KB log, right? So what is KB log? KB log omega. I ask you to pay attention on one here. All right, so this is KB log omega. The expression is given here. So this is 8. Okay, log of omega. Okay, that expression is this sum over k nk log gk divided by nk plus n. Okay, so let's spend a bit more time on this. This one is C, the red color box. Maybe a few slides, two to 3 slides earlier. Okay, and next, what do I want to do? I want to deal with this log. Right? This you also know. This combination GK divided by NK. This is something here. GK divided by NK. Yes, GK divided by NK. Okay. So this is the expression that we will need. So basically, this is from the expression from NK, from the expression of NK. Okay, so I have a KB. And here I have sum over K. NK I don't want to touch. And then I want to deal with this log. We will use the expression of NK. Now you can show by yourself that this will be a log of A minus log of A plus okay, I don't want alpha anymore. I just use A. Okay. So wait a minute, where's my n? This n is here. I will still have this n. This is entropy. Okay, so again, I want to make things easier for you when you revise. So I replace this by this. Okay, so what do I have? I have minus log of A. I have this sum over NK again. I don't want to ask you again. This is n. Okay, so the first term will give me n. KB, I have a minus sign. So this is a constant times the sum over NK. So I will have the constant. Sum over NK is n. Okay, and then this sum over NK also C epsilon K, and that will give me U. This is here. Okay, so the second term will give me U divided by KBT. Okay, and all this will we'll see the KB plus this N. Okay. All right, I think I have given you the key steps. So here we are here. And the next is last time I didn't do, when we talk about the localized particle, I didn't do all these steps. So this time I will try to provide a little bit more. Now, the next step is to look at how to deal with log A, this log of A. Okay, so I will have KB, I have minus N. What is log of A? Log of A, if you take this line here, log of A is log of N minus log of partition function, right? Because you take the log of N on both sides. So log of A, you can express it in terms of the partition function again. So that would be log N minus log of partition function. This is this really requires some experience. So this is this guy here. Okay. Plus plus U divided by KBT plus N. Okay, so I have KB, I have N times log of partition function, right? This term times this term. And then that is the thing I want to say. So I have this N log N, and I have a plus N here. So I can reverse, I can do the reverse Stirling. So this doesn't change. Okay, and that is the key result. Okay, so this guy will give me N factorial, right? So let's write out the full expression. So this is a full expression. If I do it this way, my S entropy, remember we are still talking about entropy. Now let me group together everything. I have NK log single particle partition function. So that's the first term. And then I will bring the energy term, which we know how to deal with. That will give me a NKB times T. And then we have a log. Okay, so this combined with the expression for U, a few lines up there. So multiply by this KB. Okay, so far, this looks like the case for the distinguishable case, right? So from here to here, this looks like the distinguishable case, except that you bring in something else. This is the new items I want to discover. That is this thing here. You have a minus KB. And what is this? This is N log of N factorial. So this guy in red is extra. Otherwise, if you look at everything written in black color, that is the same as before. Okay, so this brings me to the claim earlier. What is my claim? My claim is this. I wanted to do, I want to unify everything by using a different view of the problem. So if I insist of using system partition function, just like what I did before, I bring n in and combine with the single particle partition function like this. This is when the whole thing breaks down for the gas. You can try, plug this in, it will not work. That's because of this extra term that comes in. Okay, so how do you fix it? The way to fix this is actually quite simple. If you take it like this, it will absorb this term and it will work. Okay, and then you can also quickly understand why we have to go all the way to entropy to discover this. Why do we not see earlier, for example, when we calculate the internal energy? There is internal energy is here. You have this derivative with respect to temperature to rescue you, because once you take the log, you take the log of Zn, you pull out this term in log, right? You have log n factorial, which is a constant. So when you pass it through the partial derivative, it just disappears. That's why you don't see it in the internal energy. But you have to keep going until you get to the entropy to see what's wrong. Okay, this is what you need to do. Okay, so if I want to use the system partition function as my description, I will have to do it this way in order to unify the whole thing. And how do I discover this? I discover it through the expression for the entropy. Okay, so if you take this for gas, you have to take this for gas. Okay, full stop. Okay, and that will be a way to link the two pictures. All right. I don't know how much you believe this. I hope you do. So in order to convince you that this is correct, everything we do is correct, I need to reproduce some famous result for you. Okay, so I'm talking about gas. And if you go back all the way to the beginning, you will realize that what I set up is this. So what I set up is I have a Hamiltonian, which only contains the kinetic energy term. So this is the Hamiltonian only contains the kinetic energy. And what is the kinetic energy term? This is a translational kinetic energy. And what is the potential energy? Potential energy is 0. Particle in a box. Okay, and what is this model? Only the translational kinetic energy. And we got all the way to this point. And now you can ask, how do I apply? Where can I apply this? And you realize this is the case describing a monatomic gas. And we are in the dilute limit. We're in the dilute limit. This eventually, hopefully, will give me something that I can recognize as the ideal gas. Okay, so let's see how far we can pursue this picture. So the next, until the end of lecture, there are lots of cool concepts. Okay, so this is a picture to describe monotonic gas. Don't need this comma. Okay, so let's do some calculations. So first, I will take this single particle partition function, keeping in mind how to deal with it when I need to link it to the system partition function. Okay, so I have this expression which I already wrote. I'm going to copy it again. So this is the continuous form of the partition function. I have this guy. And for us, we can integrate from 0 to infinity. This is how we have our energy levels, right? So our energy levels will start from 0 all the way to infinity. And what is this G of E? So this is the same expression, this G of E. Let me be a bit lazy, and this is this guy here. This guy. Okay, so this is where G of E is this. Okay, so this is for dilute gas, and we only have kinetic energy. So let's see what we can get. We just plug this in and start to do the integration. There's all this constant to manipulate. You can do it yourself. It's rather trivial. Okay, so I will just write down all this constant for you. H cube. So I have 2m kBT. This I can pull out from the integral. Then I will have this inside the integral. I will have this times this factor. Okay. You can see this is I did it very quickly. I just copy it. So, but you can see this must be correct, right? So I have this is the density of states is proportional to square root of energy. This is a famous factor, and this square root of energy retains. And I have this Boltzmann factor, and the rest is just really manipulating the constant. Okay, and then manipulating the constant in a way that I want to have this form, because this is a standard integral. I can call this thing, I can call this x squared. Right? Once I call it this x squared, I can, this is a standard integral. I will write you the standard integral. You need a few lines of manipulation, right? Because this is from 0 to infinity, but the standard integral is from minus to plus infinity. Okay, so you have this standard integral to deal with. Dx. And this will give you square root of pi divided by 2. Okay. Okay, so please try it. I already give you all the recipe, you can do it. And this is the form I want. In the end, you have this B, volume, multiplied by 2m pi kBT divided by h squared, Planck constant square. Okay, so this is the form I want. Okay, let me say this again. There's nothing too magical. You just have to be very careful to manipulate the limits of the integral and very careful to change a variable, and you will get this expression. I guarantee you, you will get this. I checked again this morning. Okay, so now one more question, quick question. What is the unit of the partition function? What is the unit of the partition function? Give me this answer in the chat. Private message. What is the unit of the partition function? This guy. Only one answer. Okay, the answer is correct. I get 2 answers. Congratulations, both are correct. This is dimensionless. Okay, this is volume. This is volume. And therefore, this whole thing here must take the unit of 1 over volume. What is the meaning of 1 over volume? 1 over volume, let's say some number divided by volume. This is a concentration. Okay, and this number is actually called quantum concentration. Okay, so this takes the unit of concentration. Okay, so now here is the clamp. So this takes unit of inverse volume, and this is volume. Okay, so naturally we can define a volume like this. Okay, there's a standard there's a question about x times e to the minus x squared, or x squared times e to the minus x squared. This is a very standard, very common question you will ask. I'm waiting for you to ask. My calculation is correct. Now, what did I do? I'm waiting for this question, and thank you for asking. I said this. Okay, the question is it correct x squared, but here should be x only, right? But don't forget, when you change a variable, you take dx, so you 2x dx is 1 over kpt d epsilon, so you have another x here. Okay, so x squared is correct. Now the question is whether this expression is correct. Basically, this is the question. So my answer is this question is correct. How do you get it right? You have to really work out this d epsilon, you get another factor of x, and then there's another x, so that together will make x squared. All right, so now coming back to here, this is called quantum concentration. This q takes the meaning of quantum. So I will tell you why this is called quantum soon. This is quantum concentration, but I want you to understand that there's a natural quantity which we can define, and that natural quantity is concentration. Okay, so then now I hope everything can be at least unified for you. It makes a lot of sense. Now, what do I call the dilute limit? Why do I care about this dilute unit, dilute system? When I talk about dilute system, everything is linked, right? Dilute system, I can also use it to describe this. Actually, this is something I don't have time to talk about. This is quite subtle. How can I justify this? This is quite subtle. I use the entropy to convince you, but don't forget we have been dealing with dilute system. So if you want to learn more, you really have to dig deeper. This is not as trivial as we think. I don't have time to go into this, but then I want to justify how I define dilute. How I define dilute, given that I now have the chance to define a concentration, naturally I would just say, when the concentration of my gas is much smaller than the quantum concentration, this is when I can use all the treatment I have. Okay, so this is also what we call the classical regime. Right? So naturally, in the other limit, everything will be different. That is when we need to use quantum statistics. Next lecture. Okay, so in the opposite limit is when I have a lot of say electrons, and I calculate, applying the mass of the electron, applying the temperature of interest, and we get n sub q. If the concentration of my electrons in my solid is much larger than nq, n sub q, I have to use Fermi-Dirac statistics. And the opposite means I can still use classical approximation, which is what I'm doing right now. So this is the concentration of the system, of the gas, concentration of the gas. Okay, so next chapter, we talk about the opposite limit when we do the quantum statistics. So now the question at the moment is, why do we call quantum? Why quantum? Why this thing is called quantum concentration? Okay, so now I will take this quantum concentration n sub q again. This is the unit of this is 1 over volume. Okay, so if I take this, right, this n sub q takes the unit of 1 over volume. So if I take the inverse and take the cube root, this will be a length, right? So this quantity is a length. So I'm going to define a length scale. I'm going to call it thermal. It's a very standard way to call this. This depends on temperature, right? This n sub q is this whole thing here. It depends on temperature. Okay, so I will write it. I will really just treat this. Take this, take the cube root. Then I will have 1 over 2 pi mkbt. This is my lambda. Okay, so the other way to say the same thing about this limiting case is this. I can also say if the particle-particle distance is much larger than this lambda, I will be in the classical regime. Makes sense, right? When they are far away, they don't really interact. So I don't really need to care too much about this. All this kind of piece together. But still, why quantum? The reason is this. If you work out the de Broglie wavelength for this problem, you find that this guy is proportional to the de Broglie wavelength. De Broglie wavelength with a proportionality constant, let's say, I don't know, I am run out of symbol, theta, with this constant to be of the order of 1. Okay, that is the reason why this is called quantum. Okay, so this set some limiting cases. You compare with you basically compare with the de Broglie wavelength. Okay, and to really show that, I would just quickly write you the de Broglie wavelength, de Bro. How do I do this? De Broglie wavelength can be found by looking at this, right? I look at the energy scale of the problem. I only have translational kinetic energy, so this is p squared divided by 2m. And suppose this is provided by thermal energy. Okay, I don't care whether it's 1 or 2 or 3/2. Doesn't matter. This is an order of magnitude. That's why I have this order of magnitude statement above. Okay, so I have 1 over 2m. Now I have to write this in terms of de Broglie wavelength. So this is h Planck constant divided by lambda de Broglie. Okay, and this is about kBt. And you rearrange, you get lambda dB to be of the order lambda t. Okay, lambda dB square will be h bar square divided by 2m kBt. Okay, so I take the square root right now, get rid of this, and you compare with this thermal. Right, you have h bar at the top. At the bottom, you have 2m kBt square root. Okay, so this is really very similar up to a factor of 1 over square root pi. Okay, so this is the justification of quantum. Okay, so coming back to this quantum concentration, this slide here. This slide. Here I want this copy and drag to the end. I will have to spend a lot of time to tidy up all this. Okay, we already know this is quantum, and now we can come back to here. Okay, this is a sidetrack. We talk about why this is quantum, and now I want to calculate U. U is kBt squared, like this. Okay, I write it down for you to so you know how to deal with this. This is kBt squared log of single particle raised to the n divided by n factorial. As I say, this will go to 0 because it will not survive the partial derivative. Okay, so this essentially is the same. I have nkbt square, this. Okay, plus 0. I will write this 0 for you. Okay, you look at this single particle partition function up there, and you ask yourself, how do I deal with this? Sorry, there's no n here. This n doesn't exist. How do I deal with this? Now, it might look complicated, but actually it's not that difficult, because when you take the log, you have a sum of a lot of terms, right? Log of this z. And the one that survives the t is the one that has the t dependence, which is temperature. And this is t to the 3/2. Okay, so when you look at this, you basically only have, you have this whole thing, but a lot of them will not survive, right? You only have this log t of 3/2, and then the rest has no t dependence, so you don't care. And that is the first highlight of this treatment. Something has to be correct, because when I do this derivative, I find I have 3/2 nkb, and I have this t divided by log t, which is 1/t. So this is the result. This is the first highlight. What is this highlight? This highlight tells you I have the standard result from the kinetic theory of gases. You learn it somewhere else. What is the standard result? The standard result is the energy. Internal energy is a function of temperature only. We know, we learned this. We even derived this. Okay, and then for this system with translational degree of freedom, for each degree of freedom, I have a 1/2 kBt. And therefore, I will have, for this particular system in 3D, I will have 3 of them. So I will have 3/2 kBt. And how many particles do I have? I have n. So this is the total internal energy. So this is also correct. Another way to say that is this treatment allows me to get the heat capacity. Heat capacity is indeed 3/2 nkb. So this really is something that should make us happy. We derive all these results, and we really finally get something that we can link back to what we learned before. Okay. All right. So again, I'm running a little bit late. You are encouraged to stay, but if you want to leave, feel free. The next thing that makes me happy is this. I ask myself, how do I get the pressure P? Okay. Now, this is a very nice question. How do I get the pressure? I just ask, how do I get the pressure? Okay, one way to get the pressure is I remind myself of my thermodynamic. Okay, what is this? Then I will have P is minus partial derivative of F respect to volume, keeping temperature constant. And in statistical, this is thermodynamics, and in statistical mechanics, I know how to write the Helmholtz function with as a function of the partition function. Okay, I'm going to write down the result for you. That has a minus sign that cancel with this. That is kBt log, particularly simple. Okay, I differentiate with respect to temperature. Okay, so this with volume, keeping temperature constant. So this kBt can be pulled out. And then I plug in the expression for this, right? I know how to deal with this now. You already know how to link the system and the single particle. All right, and again, you know this is 0. I just have to write it down to remind you. And finally, you are at the time, you are right now, you are able to, now this n is also constant, I put it out. You are able to do this because this is the same thing. You go to look at the single particle partition function again, and you look at which term depends on v. And this v is written for you in a very, very big font. Okay, if you take log, you have log v plus log of a bunch of stuff that you don't care. Okay, so there is d by dv. Okay, this n I already pull out. This guy will be log v plus a bunch of stuff I don't care. So this is with respect to constant temperature. Other things are constant. And you get n kb t. Log v is 1 over v. And this is another happy moment. This is the equation of states for an ideal gas. Okay, so this is ideal gas, something you know. So what we have done so far really correctly give us the equation of states of the ideal gas. So that makes me comfortable with what I've done. All right, so on Wednesday, we will talk about what went wrong if we didn't look after the partition, if we are not careful with the partition function. Okay, so on Wednesday, we look at the entropy. That is the major thing that we need to be really careful about. All right, sorry for the bit of delay, and thank you very much. That's the end of today's lecture.